Okay, right, so welcome back to this next video in which we are discussing schizophrenia and the antipsychotic drugs. Okay, right, so we've now discussed the dopamine systems within the brain. Particularly, we've looked at the ventral tegmental area, which is involved in these two important pathways. The mesocortical pathway, in which dopamine neurons in the ventral tegmental area send their axons to the cerebral cortex through the medial forebrain bundle and then on to whichever portion of the cortex you go to. Okay, and then also the mesolimbic pathway, which is this pathway by which neurons in the ventral tegmental area send their axons into the nucleus accumbens on either side. Okay, and we're going to see what function that has in a moment. Okay, it's going to have a very important function in deciding what's important potentially. Okay, right, so now what we're going to talk about is the dopamine hypothesis of schizophrenia. Okay, and I'm going to give you the most up-to-date dopamine hypothesis of schizophrenia. Okay, now those of you who know something about schizophrenia already and the dopamine hypothesis, if you only know the sort of most basic form of this theory, you might think, wait a second, he's barking up the wrong tree when I first say this. Okay, because those of you who know something about schizophrenia will know that it's because of too high dopamine. Okay, but I'm about to tell you that originally dopamine starts off too low. Okay, so just bear with it basically. I do know this dopamine hypothesis, I'm not totally barking up the wrong tree. Okay, right, so the dopamine hypothesis, the full dopamine hypothesis as it stands at the moment is this. Okay, so the DA hypothesis for short. DA is often an abbreviation used for dopamine. Okay, right. So, the dopamine hypothesis then. The hypothesis is that it starts off with some sort of problem in the ventral tegmental area. Now, this is the start of the hypothesis. We don't know what actually causes this initial problem with the ventral tegmental area. Okay, this is the place where it starts. Okay, so something goes wrong with the ventral tegmental area, particularly the neurons which are giving their axons to the cortex. Okay, so really something goes wrong with the mesocortical pathway. Okay, so something happens to the mesocortical pathway, whether it's on the level of the ventral tegmental area or maybe it's on the level of the axons. Something goes wrong with it and you start getting less dopamine arriving at the cortex. Okay, so the dopamine going to the cortex is going down. Okay, and make sure you understand that it's the mesocortical pathway that's going wrong, not the mesolimbic pathway. That's initially fine. Okay, so dopamine hasn't gone down in the nucleus accumbens, it's gone down in the cortex. Okay, this now persists for absolutely ages, maybe years, okay, and it causes problems, basically. It causes problems all over the cortex is the idea. Okay, so dopamine being too low in the cortex causes problems in the cortex, okay, is the next idea. Problems in the cortex. Okay, and these problems in the cortex, for instance, include the problem with the dorsolateral prefrontal cortex, i.e. that is a problem that stems from the being too low dopamine in the cortex. That's what the dopamine hypothesis says anyway. Okay, whether it is true is a different matter. Okay, so dopamine is too low in the cortex and this causes all sorts of problems in the cortex, and these problems in the cortex then cause the negative symptoms of schizophrenia. Okay, so the negative symptoms and also the cognitive symptoms. Okay, now you remember when we initially discussed the symptoms of schizophrenia that the first symptoms to arise were the negative and the cognitive symptoms, okay, without the positive symptoms. Remember, this was known as the prodromal symptoms. Okay, so people who are going to develop schizophrenia firstly get the negative and the cognitive symptoms. Okay, the dopamine hypothesis can explain that. It says that long before you actually get the positive symptoms, dopamine going to the cortex goes down, and this causes gradual deterioration in certain aspects of the cortex, okay, and that this deterioration is what drives the negative and the cognitive symptoms. Now remember, we could explain two of the cognitive symptoms. We could explain the problem with working memory and the problem with executive function as problems on the level of the dorsolateral prefrontal cortex, okay? Remember, the volume of the dorsolateral prefrontal cortex goes down, okay, because the number of synaptic connections is going down, okay? The dopamine hypothesis asserts that the reason for that is that dopamine to the cortex is too low, okay? So that's what causes the negative symptoms. Now, this goes on for years and years and years, okay, and the disease gets worse and worse and worse, and the prodromal symptoms gets more and more exaggerated, until at last you're going to start getting the psychotic symptoms, the positive symptoms. Now, why does this happen? Well, basically, what you need to understand is that the ventral tegmental area is not a law unto itself, okay? It is controlled by other things, okay? Particularly, it is controlled by the cortex, okay? So the cortex controls the ventral tegmental area. So the idea is that because of the extremely low dopamine in the cortex that is causing gradual misfunction in the cortex over this long period of time, that eventually something will go wrong in the control that the cortex has on the ventral tegmental area. Okay, so what's now going to happen is the control that the cortex has on the ventral tegmental area is going to go down, and you're effectively going to release the ventral tegmental area. Okay, so the cortex was controlling the ventral tegmental area. It was stopping the neurons in the ventral tegmental area from overfiring. Okay, and the hypothesis now says that once the control that the cortex had on the ventral tegmental area is lost, what will happen is the ventral tegmental area will fire too often. So the neurons in the ventral tegmental area will fire too often, and they're going to now over-release dopamine, and specifically they now over-release dopamine into the nucleus accumbens. Okay, so what now happens is, because the cortex has lost its control over the ventral tegmental area, the ventral tegmental area now overactivates the mesolimbic pathway, okay, and the nucleus accumbens is going to get far too much dopamine arriving in it, okay? And too much dopamine in the nucleus accumbens is what then causes the psychotic symptoms, okay? So this causes the hallucinations and the delusions of schizophrenia, and now you have the full-blown schizophrenia disease. Okay, once these psychotic symptoms have arisen. Okay, so that is the dopamine hypothesis as it stands at the moment, that it starts off years and years before you ever get the disease with problems with the mesocortical pathway, which cause the gradual problems on the cortex, okay, which then lead to the negative and cognitive symptoms of schizophrenia building up and up and up. Okay, the problems with the cortex then result in the loss of control of the ventral tegmental area. The ventral tegmental area now overactivates the mesolimbic pathway. Okay, you get far too much dopamine in the nucleus accumbens, and this causes the psychotic symptoms, the delusions and hallucinations. Now, what I would like to add to this theory is, how does too much dopamine in the nucleus accumbens cause the psychotic symptoms? How does it cause hallucinations and delusions? Okay, well, the best theory for why this occurs is the aberrant salience hypothesis. Okay, so basically the idea is that dopamine going up in the nucleus accumbens is the system that attaches importance to things. Okay, so when something is important, the idea is that dopamine will be released into the nucleus accumbens, and that signals importance. Okay, so the idea is, in schizophrenia, if dopamine is always ridiculously high in the nucleus accumbens, then what will happen is you're going to attach importance to loads of things that shouldn't have importance attached. Okay, now this would explain the delusions of reference that are very common in psychosis, okay, which, remember, mean that you think that everything is important, everything is related to you, everything has a message, basically. You walk past a blade of grass, maybe, or a patch of grass, let's say. You decide that that patch of grass is here to send you a message, or something along those lines, okay? You might be sitting in a room and everyone else is completely unaware of the traffic outside. You can hear the traffic, okay? You think that that traffic is being driven by someone who needs to come and see you, okay? Everything is important all of a sudden, okay? So you attach importance to things that just should not have importance attached to them, okay, because of the continuously high dopamine in the nucleus accumbens, and this could lead to the delusions of reference. Okay, it could also lead to the delusions of paranoia. Okay, so paranoid delusions, because you now think that everyone's watching you, again because you're attaching importance to people. Okay, you think that everyone's against you because you're attaching importance to them. Okay, so this could also be explained by aberrant salience. Okay, potentially even auditory hallucinations could be explained by aberrant salience. Okay, now this requires a little bit more of a leap of faith. Okay, this is the most loose one. Okay, the idea is this: potentially our brains are continuously generating auditory hallucinations, okay? So potentially in a healthy person, your Wernicke's area might just be spontaneously active, even though, okay, it might have activity in it, even though there is no auditory stimulus, okay? So maybe that's normal, maybe the parts of our brain are rehearsing, okay? Maybe they're rehearsing processing sounds, okay? And usually we don't become consciously aware of it. Okay, maybe our brains are doing subconscious rehearsal and usually we don't become aware of it. However, if you've got aberrant salience, maybe what happens is suddenly the high dopamine attaches importance to those processings that are happening that should be subconscious in Wernicke's area, okay? And maybe that then is driving those to conscious attention, and then you hear them as auditory hallucinations, okay? So the idea there is potentially it's perfectly normal for Wernicke's area to be making up you know, auditory stimuli that aren't actually present, okay, to practice processing maybe, okay? But the aberrant salience then leads to these non-real signals being given far too high importance and then being actually given to conscious awareness as real auditory stimuli. Okay, so potentially the too high levels of dopamine, well, we know that the too high levels of dopamine in the nucleus accumbens seem to drive the auditory hallucinations, but maybe it's through this aberrant salience, which is promoting these normal processings to actual conscious awareness. Okay, right. So that then is the dopamine hypothesis of schizophrenia. Okay, now what we want to turn our attention to is the antipsychotic drugs. But before I talk about the antipsychotic drugs, I just want to mention one other drug which was one of the basis for the dopamine hypothesis of schizophrenia. Okay, so the drug that I want to mention is amphetamines, okay, and it's not just one drug, it's a class of drugs, okay. So, amphetamines, basically they are capable of inducing the psychotic symptoms of schizophrenia, okay. So these drugs are capable of inducing auditory hallucinations, okay, as well as delusions, okay. So, very similar symptoms to those of psychosis. Okay, now, what does this have to do with the dopamine hypothesis? Well, guess what amphetamines do? Okay, they cause massive release of dopamine into the nucleus accumbens. They work on the dopaminergic neurons of the mesolimbic pathway, and they cause them to release dopamine. Okay, not just the mesolimbic pathway, they also act on the neurons of the mesocortical pathway. Basically, they just cause dopaminergic neurons to release a huge amount of dopamine. Okay, so you get a huge huge amount of dopamine in the nucleus accumbens, and guess what happens? You get psychosis, basically. Okay, so this is drug-induced psychosis rather than schizophrenia-induced psychosis. Okay, so that's one of the leading pieces of evidence, well, it was one of the first pieces of evidence in favour of the dopamine hypothesis, and really it's what drove the entire hypothesis. Okay, backing up this initial piece of evidence are the antipsychotic drugs, because all of the antipsychotic drugs are D2 antagonists. Okay, so you remember me telling you that the receptors that you have in the neurons, on the neurons of the nucleus accumbens are D2 receptors. Well, basically, all of the antipsychotic drugs work by binding to D2 receptors and blocking them. Okay, so blocking dopamine from being able to bind to them, and I'll discuss that in a bit more now. Okay, so antipsychotic drugs then. Okay, so we'll start off with the first antipsychotic drug that came about. Okay, so the first antipsychotic drug was a drug known as chlorpromazine. Okay, right, now chlorpromazine is what's known as a phenothiazine. Okay, so I just want to show you the structure of a phenothiazine because it's quite a common structure that you'll see in many different drugs. Okay, so we might as well discuss it. Okay, so phenothiazine. So basically it's a really beautiful structure, phenothiazine. What you have is two benzene rings on either side. Okay. Oh, and by the way, a phenothiazine structure, you know, it's a structure that's in loads of different molecules. Chlorpromazine is a phenothiazine because it contains the phenothiazine structure, which I'm about to show you. So, the phenothiazine structure then, you have two benzene rings on either side. Okay, so here's one benzene ring, here is the second benzene ring. Okay, like so. And now what you're going to do is connect these two benzene rings by a nitrogen atom and by a sulfur atom. Okay, so here's a nitrogen atom and here's a sulfur atom, and then you're going to have a hydrogen off that nitrogen atom to take it up to the 3 bonds. Okay, so this is the structure of a phenothiazine. Okay, and chlorpromazine is going to be based on this structure. Okay, hence why it's known as a phenothiazine. Okay, so chlorpromazine was the first antipsychotic drug, and as I say, it is what is known as a D2 receptor antagonist. So I just want to make sure everyone understands exactly what an antagonist is. So basically, an antagonist molecule is a molecule which will bind to a receptor and not stimulate it. Okay, so if I draw the D2 receptor here, so remember the D2 receptor is a G protein coupled receptor, so I've drawn it sitting in a cell membrane, and now I'm drawing the cell membrane as 2 layers, remember, because a lipid bilayer is actually 2 layers of phospholipids. So I've promoted the membrane from being represented just as 1 line to being represented by 2 lines. Okay, so here is our D2 receptor, let's say. Now, an agonist molecule, such as dopamine, binds to the D2 receptor, okay, and then causes some conformational change in the D2 receptor that then enables the D2 receptor to interact with the heterotrimeric G protein. And you'll remember that the D2 receptor interacts with the GI heterotrimeric G protein. Okay, so that's what an agonist does. What does an antagonist do? An antagonist molecule is a molecule which binds to the receptor in the same binding site as where dopamine binds. Okay, so here is the D2 antagonist, so maybe it's chlorpromazine here, so it will bind to the D2 receptor at the same site as where dopamine would bind, and it does not induce that conformational change that then enables the D2 receptor to interact with the heterotrimeric G protein. So it doesn't activate the receptor, but it blocks the dopamine from being able to bind, okay, and therefore blocks the dopamine from being able to stimulate the D2 receptors. Okay, so effectively what it does is it stops dopamine from being able to stimulate its receptor without actually doing anything to the receptor itself, so it doesn't activate the receptor itself. Okay, so that's what's meant by a D2 antagonist. All of the antipsychotic drugs are D2 antagonists. Now, why does this work? Well, Remember, the receptors in the nucleus accumbens are D2 receptors. If you give an antipsychotic drug, all of those D2 receptors are going to end up with the antipsychotic drug bound, or at least a good fraction of them are. Okay, now the dopamine that's being released by the mesolimbic pathway is not going to be able to activate those D2 receptors, and therefore it doesn't matter that there's too much dopamine in the nucleus accumbens. If the dopamine can't actually work on its receptors, it's not going to do anything, okay? And remember, it was the too high dopamine in the nucleus accumbens which caused the psychotic symptoms of schizophrenia, okay? It caused the auditory hallucinations, it caused the delusions, okay? So now, what happens is you give this drug and it gets rid of the psychotic symptoms, and they are fantastic at getting rid of the psychotic symptoms, okay? They are fantastic drugs, antipsychotics. Before the advent of antipsychotics, nearly all people with full-blown schizophrenia were hospitalized, okay, permanently in psychiatric hospitals. Okay, now they are capable of staying free, basically, okay, because of antipsychotic drugs which can stop the psychotic symptoms. The problem is that although they are fantastic at getting rid of the psychotic symptoms, they do nothing, well, very little, to help the cognitive symptoms or the negative symptoms as well. And remember, they can't really, because if we trust the dopamine hypothesis said that all of that has happened years before you actually started getting the psychotic symptoms. Okay, and the psychotic symptoms are all that we're targeting here. We're just stopping the dopamine from acting on the nucleus accumbens. Okay, we're not repairing all of the damage that has been done to the cortex by having too low dopamine in the cortex for years and years and years. Okay, so we're not repairing all of that damage, and that's the damage that's causing the cognitive symptoms and the negative symptoms. Okay, and there are no drugs that can reverse that damage as of yet. Okay, right, so that's why the antipsychotic drugs, all of them, only get rid of the psychotic symptoms, so their name truly is true. They are antipsychotics, they are not anti-schizophrenics. Okay, right, so now let's talk then about some more antipsychotic drugs. Okay, so chlorpromazine, the first ever antipsychotic drug, is grouped with some other drugs, okay, and they're collectively known as the first generation antipsychotics. Okay, now the first generation antipsychotics, they are fantastic at getting rid of the psychotic symptoms. Okay, the problem is they have significant side effects, okay, and when I say significant side effects, I mean significant side effects. They are horrible, the side effects that I'm about to describe, okay. So the ones which have horrible side effects are grouped together as first generation. So chlorpromazine is a first generation antipsychotic. The other notable example is haloperidol. Okay, and both of them are D2 antagonists. Okay, that's the case for all antipsychotics. Every drug that I talk about now is going to be a D2 antagonist. Okay, so those are the first generation antipsychotics then. Now I'm going to talk about the next generation antipsychotics. Now, they're not usually called the second generation antipsychotics. Instead, they are called the atypical antipsychotics. Okay, now, to an extent, these atypical antipsychotics have fewer side effects. Okay, so the side effects are generally less severe. Okay, now I'll explain why the side effects are less severe when we've actually discussed the side effects. Okay, in addition, the atypical anti-side effects to some extent help with the negative and cognitive symptoms. Okay, and that's because apart from just being D2 antagonists, they have activities at all sorts of other receptors as well. And the claim is that by having these activities at all sorts of other receptors, that they help with the negative and cognitive symptoms. To be honest, they are still really only good against the psychotic symptoms. But the nice thing about them is that they do have less extrapyramidal side effects. Okay, so the atypical antipsychotics then, the main one is clozapine. Okay, but some other examples include olanzapine. Okay. And then also risperidone, okay, and then also sertindole, Okay, risperidone. And then finally, also sertindole. Okay, right, so those are 4 atypical antipsychotics now. And again, I will reiterate, they are all D2 receptor antagonists, and the best theory of how they work is that it is by being D2 antagonists, i.e. by blocking the action of this too high level of dopamine within the nucleus accumbens. Okay, right. So, those now are the antipsychotic drugs. What we want to now move on to is discussing the extrapyramidal side effects. Okay, so this is by far the most severe side effect of taking antipsychotic medication. Okay, and it's the only side effect that I'm going to talk about. It's the extrapyramidal side effects. Okay, so firstly, what does extrapyramidal mean? Okay, so basically, they are called the extrapyramidal side effects because they are going to these antipsychotic drugs are going to affect a motor system called the extrapyramidal motor system. Okay, now why is it called that? Well, pyramidal refers to the pyramidal neurons, okay, those pyramidal cells that we talked about before that are in the cerebral cortex. Okay, so most of the motor system is within the cerebral cortex, okay, and that's what the pyramidal refers to. It refers to the motor system that's within the cerebral cortex. Particularly, it refers to the primary motor cortex, which has pyramidal neurons which send their axons down in the corticospinal tract, down the spinal down the spinal cord, okay, to the motor neurons, which they then synapse on and activate movement that way. Okay, but there is another important component of the motor system, which is not a part of the cerebral cortex, and this is known as the extrapyramidal motor system. And it's this extrapyramidal motor system that we're going to see side effects emerging in with regards to these antipsychotic drugs. Okay, but I think we'll actually call it there for this video, and we'll discuss the extrapyramidal side effects of antipsychotic drugs in the next video.